again, everybody, and welcome to another Terzaghi Day. This is the 8th year that the Geo-Institute of ASCE has celebrated the birth of Karl Terzaghi, who would have turned 140 years old today, were he still with us. We do a lot of fun things on Terzaghi Day. Hopefully you follow us on social media. You can see the various posts that we have throughout the day, including a reposting of some old articles celebrating Terzaghi. We have a new blog this afternoon from the Geotechnical History blog that will focus on Karl Terzaghi's publications. And the centerpiece of it all is what you are watching right now, our Terzaghi Day live stream. We are thrilled this year to have John Burland with us from Imperial College London, and we will get to John's presentation in just a moment. In the meantime, I am, of course, Brad Keeler from the Geo-Institute. If you don't know anything about the Geo-Institute, we're happy to have you today. After you watch today, you should head over to geoinstitute.org, and there you will find out that we are a technical society with about 12,000 members, most of whom are geotechnical engineers and/or geologists, and that we are part of the American Society of Civil Engineers. A couple more things you might want to do. If you like what you see today, and I think you will, you should click like, subscribe, and get notifications, and we'll let you know every time we post something to the YouTube channel. Since it is Terzaghi Day, I have my Karl Terzaghi bobblehead with me here. We have about 20 of these Karl Terzaghi bobbleheads remaining from that big order we put in a couple of years ago. If you would like your very own Karl Terzaghi bobblehead, you can get one by going to geoinstitute.org and clicking on Student Participation Fund and making a $96 or more contribution to the Geo-Institute Student Program Fund. We will send it out to you. As long as you live in the US or Canada, we can ship it to you, no problem. You could also choose a lovely pair of Geo-Institute socks with the shield on it and everything. They're wonderful too, but today the focus is on Karl Terzaghi. One more thing before we introduce our speaker today. We are very fortunate to have a sponsor for Terzaghi Day, and it is Geopier. We have a little message for you viewers now from them. Thanks again to Geopier for sponsoring Terzaghi Day this afternoon. They've been with us for a couple of years, and we really appreciate that. So now we're on to the main event, Professor John Burland. He was born in the UK and educated in South Africa and studied civil engineering at the University of the Witwatersrand. He returned to England in 1961 and worked with Ove Arup and partners for a few years. After studying for his PhD at Cambridge, John joined the UK Building Research Station in 1966, became head of their geotechnics division in 1972, and assistant director in 1979. In 1980, he was appointed to the chair of soil mechanics at Imperial College London in succession to Professor Alan Bishop. He's now emeritus professor and senior research investigator at Imperial. In addition to being very active in teaching and research, John has been responsible for advising on the design of many large ground engineering projects worldwide. He specializes in problems relating to the interaction between the ground and masonry buildings. He was London Underground's expert witness for the parliamentary select committees on the Jubilee Line extension underground railway and has advised on many geotechnical aspects of that project, including ensuring the stability of the Big Ben clock tower. He was a member of the International Board of Consultants advising on the stabilization of the Metropolitan Cathedral of Mexico City and was a member of the Italian Prime Minister's Commission for stabilizing the Tower of Pisa. He has, of course, received many awards over the years, including the Gold Medal for Engineering Excellence of the World Federation of Engineering Organizations and the Gold Medals of the UK Institution of Structural Engineers and the UK Institution of Civil Engineers. In 1994, he was awarded the Kevin Nash Gold Medal of the International Society of Soil Mechanics and Geotechnical Engineering. In 1996, he was awarded the Seed Medal of the American Society of Civil Engineers. He's a fellow of the UK Royal Academy of Engineering, the Royal Society of London, a member of the US National Academy of Engineering, and was appointed Commander of the Most Excellent Order of the British Empire in 2005. I suspect there were a lot of things that were left out there too. What a spectacular career. We are so excited to have Professor John Burland with us today to talk about the legacy of Karl Terzaghi. John, thank you for doing this and welcome.
Thank you, Brad. It really is a huge honor to be invited to do this. And I'm looking forward to sharing ideas with you. And the other thing that it's done is it's given me an opportunity to reflect on and to share with you how much I actually owe to Terzaghi in the development of my own approach. It really is a great honor. And I found his approach incredibly helpful in my teaching, but also in my consulting. And it's really that aspect of it, the consulting and the teaching that I learnt from Karl Terzaghi that I want to share with you. And I think that the title I've chosen, Terzaghi Back to the Future, reflects my own belief that we still have a lot to learn from his writing and his way of working. And it's frequently drawn on, and one that I think hopefully you'll relate to. Now, he's known very much as the father of soil mechanics, but I think that it's very much more than that, because he was an expert in rock mechanics. He was expert in the design and construction of major geotechnical works. And I would say that he's actually the father of geotechnical engineering, and not just soil mechanics, which of course is the science that we're dealing with. So I thought it would be interesting just to reflect on his struggles to develop and establish the discipline and the art and science of the geotechnical engineering. So if I could have the next slide, please, Brad, that would be helpful. Thank you. That's the way. Yeah. And now he was born in Prague in 1883, and Dick Goodman has written this book illuminating and thoroughly researching the narrative of his life, Engineer as Artist. And I'm sure many of you have read that book. It's really an excellent one. In fact, he doesn't come across as a very lovable person, but many geniuses don't. Actually, quite often they don't. And I had many discussions with the late Professor Sir Alex Skempton about Terzaghi, who knew him very well. And Skem said that we have to distinguish between his professional life, where he could actually be harsh and even brutal at times, but his private life, he showed intense interest and charm with the people that he was dealing with. So I thought that was an interesting reflection on Terzaghi. He read mechanical engineering at the Technical University of Graz, but he was much more interested in geology, and that's extremely important. He was very keen on climbing, and it is related that when climbing on expeditions, he would turn the whole thing into a joyous adventure in geology, which I think is a lovely description, a joyous adventure in field geology. And then he switched to civil engineering and went to work with a firm specializing in hydroelectric power generation. And although much of this activity was in the design of reinforced concrete, the planning of the structures was intimately involved with the geology. Frequently, he found that the guidance of expert geologists was not helpful. He encountered many cases of failures, significantly mainly due to lack of the ability to predict and control groundwater. But there were also many piping failures all over the place, slope failures, bearing capacity failures, and excessive settlements. So that was really his first encounter with the problems of the ground. And recognizing the obvious influence of geological factors, he then concluded that it was necessary to collect as many case records as possible and to correlate the failures with the geological conditions. That was his objective. And it's very well known that he then spent 2 intensive years, that's from 1912 to 1914, in the Western United States, observing and recording. 2 years that actually ended in disillusion and depression. And that was, of course, confounded by the early part of the First World War. Could I have the next slide, please? Now, this is a quote from his presidential address to the 4th International Conference on Soil Mechanics, which really summed this up. At the end of 2 years, I took my bulky collection of data back to Europe. But when I started to separate on the work, I really couldn't separate the wheat from the chaff at all. And I realized that in fact, there was practically no wheat at all. That was his description of it. So he felt at that stage that his 2 years of hard labor were a complete disappointment, and nothing was worth publishing on its own. And my conclusion from that really is that geology on its own is not very helpful. That was certainly his experience. And also so much for precedent and case histories, literally on their own. It's all got to be knitted together much more than that. Next slide, please. And Goodman quoted on this. He said the reason for this was that the names that geologists give to different rocks and sediments have developed mainly from a scientific curiosity about the geology origins of these materials, whereas Terzaghi was aiming towards discerning the differences in their engineering properties. So that was a big disappointment. Shortly after his appointment to the Royal Ottoman Engineering University in Constantinople in 1916, he began to search the literature for insights into the mechanical behavior of the ground following this disappointing 2 years. He became increasingly frustrated because what he witnessed was a steady decline from 1860 in recorded observations and descriptions of ground behavior. What he says was that this was replaced by myriads of theories postulated and published without any adequate evidence. The need for rigor is coming through in these statements from him. So his experience must have been uppermost in his mind when, in his presidential address to the 1st International conference on soil mechanics, he stated the following, and if I can have that next slide, we can read his statement, a very important one. This is typical Terzaghi. In pure science, a very sharp distinction is made between hypotheses, theories, and laws. The difference between these categories resides exclusively in the weight of sustaining evidence. On the other hand, in foundation and earthwork engineering, everything is called a theory after it appears in print, and if the theory finds its way into a textbook, many readers are inclined to consider it a law. That's a very typical sort of Terzaghi statement, and it reflects very much his thinking at that time. So what Terzaghi is doing there is emphasizing the enormous importance of assembling and examining factual evidence to support empirical procedures. He's also bringing out the importance of instilling rigor, and rigor comes into his work time and time again. So rigor is often equated with mathematics, but certainly in my view, and it certainly was Terzaghi's, rigor is at least important, just as important, in observing and recording physical phenomena, developing logical argument, and setting these out on paper clearly and precisely. So rigor is one of these words that's going to pop up time and time again, and it's such a lesson we can learn from Terzaghi. Could I have the next slide, please? Now, in 1918, Terzaghi began to carry out experiments on forces against retaining walls, and he then moved on to piping phenomena and the flow beneath embankment dams. And he used Forchheimer's flow net construction to analyze his observations and apply them in practice, methods which were themselves adapted from the flow of electricity. And over this period, Terzaghi came to realize that geology could not become a reliable and helpful tool for engineers unless and until the mechanical behavior of the ground could be quantified. And this required a systematic set of experiments. And on a day in March 1919, on a single sheet of paper, he wrote down a list of experiments which he wanted to perform, which needed to be performed. And Terzaghi then entered an intense period of experimental work in which he carried out odometer tests and shear tests on clays and sands and developed his physical understanding of effective stress, excess pore water pressure, and the time rate of consolidation. And that at that time was really March 1919 onwards. That was the birth of soil mechanics as a rigorous science. And to make headway with the consolidation, modeling of consolidation, he turned to the mathematics of heat conduction. And we see here the interplay that went on between experiment and analytical modeling. That's very clear from his work right from the start, this interplay between rigorous analytical modeling and experiment. Now, on the slide here, we've got the book, a lovely book, actually, From Theory to Practice in Soil Mechanics. And it's a collection of some of the writings of Terzaghi. And there's some lovely illuminations in there and writings dwelling on various achievements and aspects of Terzaghi's work. by Bierham, by Casagrande, by Peck, and by Skempton. It's an absolute treasure. Now, after obtaining my bachelor's degree at the University of the Witwatersrand, I worked for a year as a research assistant to Professor Jerry Jennings, who knew Terzaghi. And one day he showed me this book. He'd just obtained it, From Theory to Practice in Soil Mechanics. And shortly after that, I spent a couple of weeks in the field in trial pits in connection with the major steelworks. And Jennings kindly lent me that book. And I spent the evenings on site, the evenings totally and utterly absorbed by it. I went right through it from cover to cover. And I think it's true to say that more than anything else, it was that book and Terzaghi's writings in it that completely fired me up and my interest in geotechnics, and it's never left me since. And yet I hardly ever see this book referred to. Now, I don't know how well known it is, but if it isn't well known, I can recommend it be republished, and perhaps the Geo-Institute might think about doing that, because it really is a treasure. It's a wonderful book. Next slide, please. Now, there are 4 distinct interlinked aspects of geotechnics, which are associated with geotechnical problems. And I sort of concluded this after a fair amount of consulting, and mainly when I had to start teaching soil mechanics. And the 4 distinct aspects are the ground profile, which includes groundwater conditions, the observed or the measured behavior of the ground, which is another aspect, prediction using appropriate models, and then empirical procedures, judgment based on precedent, and what I've called well-winnowed experience. And I got that term well-winnowed after Terzaghi referred to the fact that when he went through all his case records, it was all chaff and no wheat. And of course, winnowing is where you're separating out the wheat from the chaff. So I chose that comment, that description of empirical work, as it needs to be well-winnowed experience based on experience and precedent. So that's an important aspect of geotechnics, and it's a vital part that one should get across in one's teaching. Now, I find that geotechnics is actually a very difficult subject, and it's regarded by many engineers as a kind of black art. And I used to think that that was because of the nature of the ground and the fact that it is a 2-phase and a 3-phase material, whereas many of our structural engineers anyway work with classical structural materials of steel and concrete and timber. So I had this view that that was the real problem with geotechnics, that it was a difficult material. But after studying the views of Terzaghi, and from really my own experience, I came to the conclusion that the main problem with conveying and teaching geotechnics was actually due to a lack of appreciation of these 4 aspects that have to be considered when tackling a ground engineering problem and how they interact with each other. And examining Terzaghi's struggle towards establishing the subject, we see that there are these 4 aspects. Now, Now, the boundaries between them really are important, and they're associated with different activities as well as different topics. And I found it helpful to look at these 4 aspects of geotechnics in the form of a triangle. So if I could have the next slide, please. So I proposed what I've called the geotechnical triangle, but I actually wonder whether it shouldn't be called the Terzaghi geotechnical triangle, because it certainly emerged from my study of his work. And in the top of the triangle, we've got the ground profile, and the bottom left-hand side, we have the observed behavior, which it could be measured, it could be deduced from back analyzing a slip, but it's to do with observation and measurement. That's another aspect. The third aspect, which is prediction and modeling, is on the bottom right-hand side. And then in the middle, we've got precedent, empiricism, and well-winnowed experience. And they're all interlinked. They're all connected to each other, and there's interaction between them, but they are distinct. They are distinct disciplines. They're distinct aspects of geotechnics. Could I have the next slide, please? So I think we can go through that triangle now, and that might have got ahead a little bit. Is that? Yes, that's right. That's the one. Let's stay with that. So the top one is ground profile, and I've got a feeling there's an arrow missing at the top. It's hidden by the screen. I can't see it, but never mind. There should be a title at the top of that slide, the geotechnics triangle, with the ground and an arrow coming into the ground profile. And what's missing in that is the genesis, the way the ground profile was formed. And it's a very, very important aspect of understanding the ground profile and its where it's come from, how it was formed. But you'll find that on the original slide, or certainly in my publications. And of course, the discipline of obtaining the ground profile is ground exploration and description, which is out to the side there in that top part of the triangle, ground exploration and description. So that's a key aspect of geotechnical engineering. And by ground profile, I actually mean the description in very simple terms, simple relevant engineering terms of the successive strata, together with the groundwater conditions and their variation across the site. Also, it's absolutely vital to understand the geological processes. That's why the genesis of the ground profile is so important. I'm actually convinced, and this is quite a bold statement, but actually I'm convinced that 9 times out of 10 major design decisions can be made on the basis of a really good ground profile description. And similarly, in my experience, 9 failures out of 10 result from a lack of knowledge about the ground profile and often the groundwater conditions. So that's an extremely important part of the triangle. We're going to see the bit going in at the top in one of the later slides. So if we can move on to the next slide, please. Right. So we now come to the observed behavior. So this activity involves observation and measurement. It includes laboratory and field testing, field observations of behavior, including movements, groundwater flow, and the development of pollution plumes, for example. It's all about observation. And it certainly includes modern satellite methods of Earth observation, which fit into that bottom left-hand part of the triangle. And these are all part of the discipline that we have of observing and measuring. Next slide, please. And here we come to what I've called appropriate modelling. Now, that term modelling is being used increasingly in engineering geology because engineering geologists are very familiar with the process of developing geological models. But I'm using the term modelling much more in terms of forming analytical models of behaviour. So the process of modelling is assembling these idealizations into an appropriate model and making a model that's amenable to analysis and hence prediction. And the important phrase here is to analyze is to idealize. So analysis is much, much more than just simply doing some mathematics. It also involves the idealizations that go into it to make it an appropriate model. Now, this process of making the appropriate model requires a lot of iteration. So you're iterating between observed behavior, the ground profile, and developing the model. The next slide, please, brings us to empirical behavior. Actually, I think we'll stay on that slide, yes. Right in the middle, we have precedent empiricism. Now, empirical procedures and experience. With materials as complex and as varied as the ground, empiricism really is inevitable. And it is, and it's always going to remain, an essential aspect of geotechnical engineers. We'll never get away from empiricism. And many of our design and construction procedures are the product of this term that I'm using, well-winnowed experience. So that is the experience that results from a rigorous sifting of all the facts that relate to a particular empirical procedure. So here we have on this slide the complete geotechnical triangle. And there are actually 5 aspects, although the top one is missing on that slide. I don't know why, but it's disappeared off the top. And it's the genesis of the ground. And each of those aspects involve distinct types of activity with different outputs. And each activity has a distinct methodology. Each has its own rigor, and I want to stress that. So we've got these 4 or 5, if we include the genesis in the top profile, these 5 rigorous activities. And I believe, and in fact, it's all derived from studying Terzaghi's work, and it reveals, I think, a coherence and an integration which is reflected in a balanced triangle. We need to balance that triangle all the time and not concentrate on one or other aspect. One person might pride themselves in their empirical approach to work, but if you're deficient in the ground profile, the observed behavior, or the modeling, then you are deficient in the tools that you're using for tackling a design or tackling a geotechnical problem. So I think that what is lovely about the approach that's evolved from studying Terzaghi is this coherence of the whole problem in that rather simple diagram. Now I want to talk just a little bit about the interaction between geotechnical engineers and civil and structural engineers, of which I've got a fair amount of experience. Could I have the next slide? Yes, I've got that. No, it's okay. I've said here there are very real difficulties in communicating between civil and structural engineers. I've tried it a lot, and geotechnical engineers. And what I've come to realize is that right at the heart of the problem is that there is a profound difference in approach to modeling the real world situation. And we can look at that in a bit more detail. If I could have the next slide, please. Yes, here are two examples I'm coming to of my interacting with structural engineers. The first one is the Leaning Tower of Pisa. And I had the privilege of being a member of the commission that was responsible for the design and implementation of stabilization measures. The commission was chaired by the late Professor Michaela Jamalkowski, and it was a very high-profile project, which was carried out under the watchful eyes of the world press. And we had a consistent of the commission. We had mainly structural and geotechnical engineers, with some architects and architectural historians, but there was plenty of opportunity for interaction between the geotechnical and the structural engineers, and it was immensely interesting. And the next slide, please. Another very high-profile project that I was involved in and was mentioned in the introduction was work at the Palace of Westminster, of which the Big Ben clock tower is part. Some years ago, many years ago, I was involved in the design of an underground car park immediately, a new palace yard immediately next to the Palace of Westminster. And you can see that underground car park to the right-hand side of that slide. And on the left-hand side is a much more recent major excavation in connection with the new Jubilee Line Metro Railway, which runs into a very large station and station box just underneath what's called Bridge Street on the other side of the road from the Big Ben clock tower. And once again, this involved huge interaction between civil and structural engineers. And I've given a lot of thought to why there is this difficulty in communicating. Could I have the next slide, please? So I've come to the conclusion that for structural engineering, when you're modeling, your material is fairly well defined, and your geometry is usually very well defined, and the uncertainties of the actual material properties and lack of fit are often overlooked. There's a tendency to believe that it's a very precise procedure, civil and structural engineering, because of the well-defined material properties. In actual fact, it's a mistake to believe that there is that precision. There are all sorts of reasons why they aren't as precise in their predictions as it appears they should be. The point is, though, that the structural engineer is working at the bottom right-hand corner of the geotechnical triangle. A lot of his work is there. And it gives rise to this rather illusory sense of precision, which isn't in fact real. And I've struggled for many years to try and explain to structural engineers what it is that geotechnical engineering is all about. And I've now found that the best way of explaining it is to ask the structural engineer to think about what is involved when he's working on a historic structure. And the processes that the structural engineer will go through are remarkably similar to the processes that we go through as geotechnical engineers. Could I have the next slide, please? And I've tried to bring that out in this slide. On the left-hand side, there is a view of the West Tower of Ely Cathedral, which is a magnificent cathedral in East Anglia, a town called Ely. And Professor Jacques Haymond from Cambridge University advised on the restoration and repair of that cathedral, and in particular of this tower. I've had many discussions with him, and I've put next to that picture a triangle which is very nearly the geotechnical triangle. At the top, we've got the top, which was the geology for geotechnics. We've got the genesis of the building. We have the genesis of the geology, which is all important. How did it get there? And the same thing about one of these ancient buildings. You have to understand how that building was constructed. It wasn't just wished in place. And then there's the whole issue of the materials, requiring a detailed examination of the materials in that tower, in that structure, and looking for defects and how that structure is made up. If we go to the other two triangles, they're very similar to geotechnics, because on the bottom left-hand side, there will be a significant amount of sampling and testing, taking samples, testing for strength and deformation, looking for imperfections, lab and field work, very similar to geotechnical testing of the ground. And then we're confronted on the bottom right-hand side with assembling and building an appropriate model for examining the stability and effectiveness of various remedial measures and so on. So once again, we would be modeling, and the properties which are measured in the bottom left-hand side and the genesis of the structure and the way it was formed feed into that model. So the process is remarkably similar to ground investigation and developing the model for geotechnical engineering. And right in the middle, of course, we have precedent, empiricism, and well-winnowed experience. And that's just exactly the same. You have to work with engineers who have experience in working with these ancient monuments. It's quite an art form. So it made me realize that that's the way to explain to the structural engineer what it is that we geotechnical engineers are all about, by drawing their attention to the processes that the structural engineer has to go through when working on a historical building. So I hope that is of interest to you, but it's certainly a revelation to me to sort of figure that out. Could I have the next slide, please? And I'm really nearly finishing now, but I do want to talk a little bit about education, because I think it's a very important aspect of the application of the geotechnical triangle. So if we can have the next slide, which I think is a repeat of the geotechnical triangle, there we are. I'm sorry that the genesis is missing from the very top of that slide. I don't know what happened there. But I found that using that triangle is a very helpful teaching aid, because students get very confused indeed about where empiricism comes in, where rigor and analysis come in, whereas this triangle clarifies the various activities that geotechnical engineering undergoes. So I found it very useful to say to the student, where are we in that geotechnical triangle now? You know, what part of that are we working in when we're dealing with an empirical method for designing a pile, for example, or we're trying to establish the geology and its importance in the design process, or when we're actually modeling, doing analysis. That's the way I do teach now. I take the students through the geotechnical triangle and tell them where we are in that triangle as we develop the work. Now the next slide, please. Civil engineering, see boring. Now, I found that statement in a London telephone directory. I looked up civil engineering and it said, see boring. And I'm afraid that in a way that statement is an all too accurate perception that the general public often have of civil engineering and geotechnical engineering. And there are many reasons for this, but I think the major one is that we fail to convey to the public and to children in particular the reality of what working as a geotechnical engineer involves, what is actually involved. I mean, most construction projects are unique. Each offers a very special challenge. Next slide, please. These are some of the challenges. Each offer very special challenges from conception right through to planning, design, and in construction. Overcoming these challenges can be very demanding. And I certainly in working with my work on Pisa Tower, I've always tried to emphasize you know, how challenging and what some of the uncertainties were, and what a challenge it all was. So we've got to avoid, I think, trying to present our work in a rather bland way, but try and convey to our public and to our readers the excitement and the challenge of the science and the art of geotechnical engineering. And I think we should try and concentrate on that more. So I've said here, in my experience, I believe that the public and young people in particular, they relate very strongly to the drama of overcoming adversity, dealing with unexpected, responding to the challenges and setbacks. And I'll have to put this in here. I was always intrigued by the way that the spectators watching Arnold Palmer used to root for him whenever he got into trouble and got himself out of trouble. And I'm not going to mention the Ryder Cup this evening. It would not be right to do so. But I find that the public and the press in particular actually do respond to being told and being taken through some of the challenges that we have to face. And usually I find the press and the public respond to it really well. And I believe that if we do start to show much more openly the real challenges of geotechnical engineering as it interfaces with nature, I think our public profile will rise and our profession will be seen to be the challenge, and will be seen to see what challenges and responsibilities are really involved in geotechnical engineering. And I'm sure in that way we'll attract the right sorts of young people to the profession. So really, to sum up, far from being boring, I think geotechnical engineering is creative, challenging, has its struggles, and very real human dramas. The responsibilities that we carry are immense. We are serving communities and working with our fragile natural environment. And Karl Terzaghi conveyed these challenges in his writings and his lectures. And like Karl Terzaghi, we need to convey this to our students and to the general public and to young people. So I hope you found that of interest, and I'm very happy to respond to any queries that you might have. So thank you very much.
John, that was really good. That was a lot of fun too. And I'll see if we have any questions coming in on the chat. If you do have a question for John, now is the time. I think you got to so much in that presentation. So there are all kinds of directions we can go with the Q&A. I'm going to start with a couple. And I think the first one, I want to ask you a couple. Well, we got to talk about the Tower of Pisa, right? I think we'd be remiss to not do that. Can you give us a quick summary of the famous story is how it was stabilized. Can you give us a quick summary of that and how you came up with the method that was used in the end?
I'll certainly give it a go. I mean, before we came on the scene as a commission, and indeed during the early parts of the work of the commission, the view was held that the reason why the tower was leaning was either that there was non-uniform ground under it, and it's leaning south, so that the ground perhaps on the south side was weaker than the north side, or that there'd been a bearing capacity failure, and that the tower was on the point of falling over due to fully development shear strength. That was the current view, and indeed Karl Terzaghi believed that as well. What was really important about our work was that measurements on the tower began in the early 20th century, and they were beautiful measurements of the change of inclination of the tower and also the settlement of the tower. And this gave us a lot of information about the way the tower was actually deforming or moving. And what came out was that the north side of the tower was coming up while the south side was going down. That was the form of the motion. Now, that is not a bearing capacity failure. There's something else going on. And what we developed from that work, and doing a lot of work on the properties of the material, we concluded that the mechanism was something called leaning instability. And it could be easily described if you watch a child building wooden bricks on a carpet. And the carpet can be quite strong, but it's very compressible. You will find, and the child will find, that you only get to a certain height, and it'll then start to lean and it'll fall over. And that phenomenon is very similar to the buckling of a strut, actually. It's called leaning instability, and basically it's due to the deformation characteristics of the ground and not its strength. It gets to a certain stage where if it moves a little bit, the center of gravity moves and you develop an overturning moment. And there comes a time when the foundations can't develop enough resisting moment to resist the overturning moment. And that's when it fails. And it's nothing to do with the strength. It's to do with the deformability. And we concluded that from the measurements that have been made on the tower. So it brings out how incredibly important measurement is. Without those measurements that had started at the beginning of the 20th century, we'd have never got to the bottom of that. Well, we might have, but we wouldn't really have got there. And once we realized that it wasn't a strength problem, it was a deformation problem, the solution then emerged. And basically, the one that we followed was to reduce its inclination a bit and reduce that overturning moment. So what we did was we straightened the tower a bit by extracting soil from beneath the high side and bringing the tower back. But it all hinged on understanding the mechanism of behavior. Without that, we wouldn't have got anywhere near it. So that's really the story about Pisa, and it brings out this huge importance of deformation and understanding mechanisms of behavior. And of course, after that, we were able to model that on the computer, and we showed that that was indeed the case. And we did centrifuge tests, which confirmed that. So in a nutshell, quickly, that's the story of stabilizing Pisa.
So I want to ask you a follow-up to that about a much lower tech model that you did of Pisa, and that was with the sponges. And I had totally forgotten about this until I announced to the crowd. I'm at the Canadian Geotechnical Society conference in Saskatoon today, and I announced to the crowd this morning when I got up to speak that we were having this event with you today, and somebody came up to me and asked about the sponge model. And I had totally forgotten about this until they did. So can you describe for everybody watching today what the sponge model was in relation to the Tower of Pisa, and where they can see this, if you know where it is?
Well, the sponge model is simply the building a model brick tower on a carpet, but instead of a carpet, it's a sponge. That's all. So that's what I use to develop leaning instability to my students. I get them to try and build a tower with bricks on a sponge, on a piece of sponge. It's foam rubber, really. That's really what it is. So anyone can do it. It's great fun, and you can witness leaning instability by building this brick tower or whatever you'd like to use on a foam rubber base. There's only a limited height you can go to, and it's the leaning instability phenomenon.
Fantastic. So Ian Gidley in the chat, who watches every one of our live streams, and we try to get to a lot of his questions, wants to know, how did you find the communication was between the geotechnical and the structural teams for the Tower of Pisa? And did you have any differences of opinion that were challenging to resolve?
Yeah, huge. This whole issue of interaction between geotechnical and structural engineers came to a head, and as I tried to describe, the structural engineering approach was to let's just put some ground anchors on the north side of the tower and pull it down, load it up on the north side and straighten the tower up a bit, and that'll do it. And it got so, I mean, there was huge strife over that, but eventually that was tried, but it was a complete disaster because to get the ground anchors in on the north side, we had to construct a ring, a temporary ring around the tower, and that involved digging in the catino around the base of the tower, which was very dangerous. And we had to freeze the ground to do that digging. And the tower, we had to abandon it. The tower wobbled and went southwards quite dramatically. It was an absolute nightmare. We call it Black September when we had to abandon that particular approach. So there was, at times, there was huge disagreement between the geotechnical and the structural engineers. And that's why I've sort of emphasized this analogy that geotechnical engineering is rather like working on an ancient building and having to understand its genesis as well as and its history. And it's not just analyzing.
So I think for a lot of people, I mean, certainly myself, you are a geo legend, and the community thinks of you as someone who will just know what to do when you go into a situation like this. The moment that you just described, was that the scariest moment of that project for that team, or were there other times where you just thought it was not going to work?
It was certainly the scariest time. It was very frightening, and there were big political issues as well, which I won't go into, but you have to be quite an astute politician working in Italy. They're great past masters on political play. But this is where Geo-Congress was so good, actually. He was able to handle it brilliantly. No, it was, I mean, there were one or two moments during the soil extraction when we got a bit worried, but I think the Black September was the most scary. That really was quite worrying.
So I feel like we could ask you about 50,000 questions about the Tower of Pisa, but we do have a few others on other topics here too, yeah. And so I want to get to a few of them. And one is fairly straightforward, but I think you're going to have a lot to say. What is one piece of advice that you would offer to an entry-level engineer, and one piece that you would give to a senior practicing engineer?
Right. Well, the new engineer, I would certainly suggest that they read up about the geotechnical triangle. It is Terzaghi, and I don't take credit for it. It emerged from my study of Terzaghi's work and my difficulties of explaining to students the difference between various aspects of the subject. They get confused very quickly between empirical and analytical methods, and the geotechnical triangle helped, I believe, conveys to them the various aspects of geotechnical engineering. So I would recommend that as a good point to start with, and I have written it up. And then, how do I deal with the senior engineer? Is this a senior structural engineer or a senior geotechnical engineer?
We'll keep it to geotech.
Right. I mean, I think that I think as long as a lot of it becomes intuitive after a while, I think I'd like them to understand the very real difficulties that the younger people have in doing geotechnics and in sorting it all out. So I suppose in a way I'll go back to the geotechnical triangle, because I think that it can be taken for granted so quickly, and it's so easy to forget how difficult geotechnics actually is. As far as the senior one is concerned, encourage the young ones to go out to site. Encourage them to flex their muscles and stride out and do give them some practical projects to work on, to build up confidence and build up experience. So I think my advice to the older ones would be encouragement. Encourage.
That's fantastic. I want to make sure we ask at least one question about Dick Goodman's book, because you're clearly a student of it.
Yes.
And I don't want to pass this up. So the title of that book is Engineer as Artist, and you had a couple of slides that alluded to examples of that. What is your favorite example of Terzaghi as an artist?
Well, I mean, I think his drawings were absolutely superb, and he was an artist. There's no question about it. He got the most beautiful drawings, and Dick has some of those in his book. And I had immediate sympathy with him because I'm very fond of drawing, and I'm very fond of art. But I mean, what Dick, I think, has captured so well, he used the word artists, and I think quite rightly, but it's a wonderful commentary on his life. That is what it's well worth reading. The difficulties people had with him, some of his, he, as I say, he could be a difficult man. He could be brutal. He could be merciless in his criticisms. And Dick has captured that. And artists can be quite sort of difficult to deal with.
I do want to ask you too. You mentioned something that's not common in any kind of engineering presentation, and that is, I guess, what you'd call public relations and dealing with the media. And you brought it up a couple of times.
Yes.
Do you feel that either one of your really huge projects, being the Westminster Palace or the Tower of Pisa, do you feel that the media attention that those got impacted the actual project itself and how you had to go about doing it?
I think they had to be very carefully handled. I'm not sure that they actually impacted the work. I think we were able to avoid that. I mean, there were times when on the Pisa Commission, we came under very severe attack by the press and by one particular individual, actually, and it proved difficult because it went right up to ministerial level. But I don't think there was any occasion when it actually affected the project. I mean, I can tell you one particularly difficult situation when we had for the underground car park, we had a little forum, a little group, about 5 engineers who met regularly, and one of them was unhappy about some aspect of the movements generated by the underground car park. And he sent an email to us all, or actually in those days it was a fax. And what he intended to say was that he was worried about some particular deformations because they could cause cracking in the Palace of Westminster. And he sent off this fax, but the number that he sent it to was incorrect by 1 digit from the number that we all had. And it so happened that the number that he used was the BBC news desk. And the phrase that he used was, "I am concerned by the movements that are predicted because they're going to cause the Palace of Westminster to move towards Big Ben Tower and the River Thames and cause failure." Now, by failure, he meant, of course, a bit of cracking, but he used the word failure in his facts. And the BBC news desk got hold of this. And it was headlines, I can tell you. There was a huge outcry on this one. It didn't change the project, but it caused huge problems. In fact, I even had a telephone from my son who lives in Japan saying, "Dad, I've just heard the news that if you carry on with the work you're doing on the underground, on the car park at Westminster, the Houses of Parliament are going to fall over." So you can imagine that sort of mistake, really. Anyway, we got through that.
That is an absolutely incredible story.
It didn't change the project. It didn't change the project, but it was difficult.
I love that. That is great. So I want to ask one final question, and we'll circle back and we'll make it about Terzaghi since it is Terzaghi Day. And I want to know your opinion on this. Do you feel that during his lifetime that Terzaghi had a sense of his stature within the community, or do you think he didn't realize what an impact he had on the field?
I'm sure he didn't realize. I mean, I think he realized he was a pretty key figure in the whole subject. He didn't hide his light under a bushel, but I'm quite certain he wasn't aware of the huge regard and the huge stature that he has now to us practicing geotechnical engineers. I very much doubt it. And he probably didn't dwell on that either. I mean, I don't think that's what he was looking for.
That is a good answer and a good place to wrap up. My wife thinks I'm crazy, but I think Terzaghi Day is probably the most fun day of the year that we have. And it's because of things like this. This was fantastic. Thank you, John, for a great presentation and touching on all of those things. This was so much more, I think, than this was just great. I really enjoyed it. Good. So for our viewers, thank you for sticking with us until the end of the conversation. I hope you enjoyed it too. We put links in the chat for some of the other things that we have going on for Terzaghi Day today. I mentioned the blog post at the beginning. That is up on the website. We'll have a couple more things throughout the day. And there's also the link in there if you did want to donate to GI student programs and get your very own Terzaghi bobblehead as well. You can do that while they last. So thanks again to Geopier for sponsoring us today. Our next live stream is going to be October 19th, and that is going to be the first of 4 sneak preview live streams for Geo-Congress 2024. They'll be about case histories in the Pacific Northwest, and this first one is about the Highway 5 collapses in British Columbia. So John, thank you again for this. This was so much fun. I'm glad you were able to work it out.
I've really enjoyed it.
A fantastic presentation. So great job. One more note. This is the Terzaghi tree that's at my house behind me, decorated with all kinds of ornaments, memorializing Terzaghi's career and Terzaghi award winners and Terzaghi lecturers over the years. So in case anybody thought I had my seasons wrong, now you have an explanation for why there's the tree behind me. So John, thanks again. For all our viewers, thanks again for sticking with us, and we will see all of you very soon, and have a happy Terzaghi Day.
Well, yes,